So we're well on the way to making a pretty good universe here. 12. Perfect vacuum contains one-state quanta and is not empty space, as we said before. 13. Elementary particle formation requires a minimum threshold energy density. Here's our initial density, as in the previous experiment, and the proton count after cooling. And we see that with the explosions that occur at very high energy densities, the number of protons resulting in the volume when it finally cools down are few compared to other areas up here. 14. The time development laws in equations 7 through 17 result in creation of 8 elementary particles. I'm using the word creation here, meaning that the random distribution of quanta, which we can seed a simulated volume with to begin a simulation, are organized in a particular way such that we see, after cooling, 8 elementary particles clearly. We're representing the states of 3 spot units in a spot, the M and the L bits in each of 3 spot units. Each row is a different pattern where the total energy of the spot is 3, meaning that there are 3 one states. So you see each row has 3 one states. So after cooling, the initially randomly seeded quanta are organized by the equations of binary mechanics into 3 left-handed d-quarks, red, green, and blue, shown here. The probability of these occurring is 20 times more than what would be expected if these quanta were randomly distributed with this number shown here, which is less than 1%. And here we're about 13%. These 3 items here are the right-handed matter d-quarks, blue, green, and red, again showing more than 20 times the probability of random distribution for these particles. Down below we have the 3L configuration where we've got the 3 bits in the L positions here for the positron and the 3 matter or M-type bits in the M locations for the electron. This is a stunning result. In other words, the equations of binary mechanics alone organize the quanta in the spot cube lattice in a simulated volume into the 8 elementary particles predicted by the spot cube model of space. The time development laws also determine the minimum energy density required, or the threshold, for creation of each particle type via quanta aggregation. Here we have one state or quanta density from rather low up here to 0.22, which is about 1/5 of the loci are populated with one states. And here we're showing on the scale here the right-handed matter d-quarks, the proportion of maximum possible. EXP is the expected result by random distribution of these items. And here's the curve in the lower right showing the expected values. Here we have 3 different orders of the bit operations, which are part of the time development laws of binary mechanics. The scalar, unconditional, vector, and strong bit operations in one order, the pink curve, and 2 other orders are shown in the other curves. Notice that the SUVF order of the bit operations produces the most matter particles. What this means is that the order of the bit operations matters. Technically speaking, the bit operations don't commute. You get different results with different orders, as this slide shows, so that One and only one bit operation order can be the physically correct one. The proton-hadron bit cycle aggregates quanta one states in adjacent spot cubes. This is a foundational principle in nucleogenesis in nuclear physics. Recall I showed you the 42 location proton bit cycle, and that part of it extended into the next spot cube above, and part of it extended to the lower left or lower right in this perspective. Now, if we flip the spot cube over and look at the other side, you can notice something, that the antimatter d quarks, which are the light blue, pink, and light green spots in the illustration, can exchange quanta with the positron spot. And the positron spot, if you look back at the 42 location proton bit cycle, is not included in the spot cube that is the home or base for that proton bit cycle. Thus, the positron spot in that spot cube would be connecting in the other directions to complete all six faces of the spot cube. All six faces of the spot cube would share energy with neighboring spot cubes. In other words, if we have a buildup of energy within one particular spot cube and its proton bit cycle, that energy doesn't get dispersed just anywhere. It's just not thrown all over the place. That energy is distributed to neighboring spot cubes by the mechanisms and by the structure of the proton bit cycle itself. This is why this analysis I'm presenting to you now is a foundational principle in nuclear physics, so that your nuclear physics books of tomorrow will probably start with this idea. 17. Aggregation of quanta in the proton bit cycle results in atomic nuclei, as we've explained, with higher atomic numbers, including the periodic table of elements and isotopes. We're making a lot of progress in making our universe here. And 2, determines the relative stability of atomic nuclei configurations. Here we're going to look at the span of energy density from absolute vacuum, 0, up to maximum, and look at proton-electron distance, which is part of the output that the simulator provides in its file output. Below the proton threshold, we have an electron-positron gas in perfect vacuum. At a certain density then, above that threshold, we start to get hydrogen, and a little later, at a higher threshold, neutrons start to be formed. Notice that in the proton bit cycle that I showed you with the 42 locations, there was nothing in the electron spot. Well, what if quanta make their way into that spot, and there's 3 of them, enough to form an electron particle? Then we have a neutron, and it has its own higher threshold for that event to occur. What we see here is decreasing distance between protons and electrons, quanta, as we increase the energy density, which means, in my opinion, that we are forming atomic nuclei with a greater atomic numbers. And there's our periodic table being formed. When we get up to a much higher density, around 0.6, we start to see that the protons and electrons start to disassociate from each other, and this is the formation, I think, of plasma. Above a certain level, we get to what we call the lepton quark soup. It turns out that the quantity of leptons is greater than quarks, and that's why it's called a lepton quark soup. Out there at CERN, they really don't have much of a good idea of what they're actually even doing. They call this, but just for reference, they call this a quark gluon soup. And by the way, they talk about proton-proton collisions up at 13 TeV energies, and this is really soup beams that they're colliding, not actually proton beams, as you can clearly see here in this diagram. Well, we've gone a long way to create our universe. A further major aggregation step is formation of molecules. 19. Chemists have done well describing processes of molecule formation. I'll leave that to them. Biologists added shock and awe with huge molecules in DNA and proteins. So, starting out with our spot unit in binary mechanics, we not only create a universe and have everything we need to create the universe, we also get up to having living things in point 20 here. Notice that all of the aggregation steps are really describing a collection of energy quanta in smaller volumes. This sounds like gravity, doesn't it? Failed gravity theories ignore all these clearly defined aggregation steps. So there you have it, folks. You start with the best theory of everything. That is the starting point for any viable cosmological model, and you get everything. Thanks for your time and attention. Have a great day, you all. It's a wonderful universe.